Welcome to Programming Fluency. This is Section 2.3, Floating Point Types. You already know how to store whole numbers. Now you will learn how C stores numbers with a decimal point like temperatures and prices. There is a surprise waiting. These numbers are not always exact. Let us see why and how to work with them safely. Numbers with a decimal point are called floating point numbers. They let you store things like temperatures and prices, but they come with a surprise. They are not always exact. Let us see what that means and how to handle it. Let us get started. Here is the plan for this video. First, we meet the two floating point types, float and double. Both hold numbers with a decimal point. They differ in precision and in how much memory they use. Next, we look at how a floating point number is stored. You will see the sign, the exponent, and the mantissa. This is binary scientific notation packed into the bits. Then we find out why they are not exact. Most decimals cannot be written exactly in binary, so the value is rounded and a tiny error creeps in. After that, we cover comparison pitfalls and the fix. You will see why 0.1 plus 0.2 is not 0.3, why the double equals check fails, and how an epsilon comparison saves you. Finally, we meet the special values, na-in and infinity. You will learn what bad math produces instead of crashing, and how these values behave. Let us start with a surprise. In C, add 0.1 and 0.2. You expect the answer to be 0.3. Instead, you get this: 0.3, then a long tail of zeros and a 4 right at the end. This is not a bug in your program. Every language that uses floating point numbers does this. It comes from how computers store numbers with a decimal point. C just does not hide it from you. C gives you two main types for numbers with a decimal point. They differ in precision. Precision means how many digits of accuracy the type carries. A float is single precision. It uses 32 bits, which is 4 bytes. It stores about 7 significant decimal digits. A double is double precision. It uses 64 bits, which is 8 bytes. It stores about 15 significant decimal digits. For most work, double is the type you want. It is the default choice. Here is how you declare each one. We make a float called temperature and set it to 98.6 F. We make a double called pi and set it to a long value of pi. Notice the letter F on 98.6 F. This matters. A plain number with a decimal point is a double by default. It is not a float. The F suffix tells the compiler to treat this value as a float. Without it, the compiler may warn you about lost precision. Now let us print them. A float prints with the format specifier %F. A double also uses %FC, promotes a float to a double when you pass it to printf, so printf always receives a double. You can also use %E for scientific notation. Pi then prints as 3.141593 E plus 00. By default, %F prints 6 decimal places. Use %.2F for 2 places, or %.20F to reveal the hidden error. So why are they not exact? Integers are exact. When you store 42 in an int, you get exactly 42, no approximation. Floating point numbers do not have that guarantee. The reason is that computers store numbers in binary, which is base 2. The value 0.1 in decimal is a repeating pattern in binary that never ends. With only 32 or 64 bits, that pattern must be cut off. The cut adds a tiny error. Let us open up a double. A double is 64 bits. Think of those bits as one long strip. That strip is split into 3 fields. We will fill in each field one at a time. The first field is the sign bit. It is just 1 bit. It decides one thing: is the number positive or negative? The next field is the exponent. It is 11 bits. The exponent sets the scale of the number, like the power of 10 in scientific notation. The last field is the mantissa. It is 52 bits, so it is by far the widest. The mantissa holds the significant digits. More bits here means more precision. Here is the consequence. Not every decimal number maps to an exact float or double. Values that are powers of 2 are exact. 0.5, 0.25, and 0.125 all store perfectly. But common decimals like 0.1, 0.2, and 0.3 do not. For a double, the error is around 10 to the minus 16. That is very small. It is tiny, but it adds up when you do the same arithmetic many times. Theory is one thing. Let us see the imprecision directly. This program stores 0.1 in both a float and a double. Then it prints each with 20 decimal places. Look at the output. Neither value is exactly 0.1. The float is accurate to about 7 digits, then it drifts. The double is accurate to about 15 digits. Both are approximations. The double is just a much better one. The imprecision becomes a real bug when you compare values. We set it to 0.1, B to 0.2, and C to 0.3. Then we ask if a plus B equals C. This prints not equal. Each value has its own rounding error. The sum lands very close to 0.3, but not exactly on it. That is enough to make the equality check false. So here is the most important lesson about floating point arithmetic. Never use the double equals sign to compare floating point values. Instead, check whether the difference between the two values is smaller than a small tolerance. We call that tolerance epsilon. Here epsilon is 1 times 10 to the minus 9, which is 1 billionth. The function f_abs gives the absolute value. If the difference is smaller than epsilon, treat the values as equal. When you use the math header, some systems need you to link the math library. You do that with the -lm flag at the end of your compile command. Floating point arithmetic does not crash on bad math. Instead, it produces special values that mean something went wrong. The first is nyan, which stands for not a number. It comes from an undefined result, like 0 divided by 0 or the square root of -1. Here is the strange part. Ordered comparisons with nyan are all false. Equals, less than, and greater than all return false. Even nyan equals nyan is false. There is one exception. Nyan does not equal nyan is true. The second is infinity. It is a result larger than any finite number. 1 divided by 0 gives positive infinity. -1 divided by 0 gives negative infinity. Here is a program that generates both special values. We make a variable 0 set to 0 and a variable 1 set to 1. Then we divide 0 by 0, 1 by 0, and -1 by 0. The output prints nan, inf, and -inf. Dividing a floating point number by 0 does not crash. On modern hardware, it produces infinity or nyan instead. And remember, nyan spreads. Any arithmetic with nyan produces nyan, so one nyan can poison every result after it. Let us see how the error grows. This program adds 0.110 times. then subtracts 1.0. Look at the two results. The float version misses 1.0 by about 10 to the minus 7. The double version misses by about 10 to the minus 16. Each addition of 0.1 adds a small rounding error, and after 10 additions, those errors pile up. Money is different, though, because neither float nor double stores a value like 0.10 exactly. Exact money is not kept in floating point at all. It is stored in integer sense, or in a decimal type. So when do you use each one? Use double when you want correct results. That is the default. Use float only when memory is severely limited. Use double for scientific or engineering work. Use float for large arrays, where 4 bytes versus 8 bytes really matters. Use double when you have no specific reason to do otherwise. Use float in GPU programming, which is often optimized for float. One important exception: do not use floating point for exact money. Neither float nor double can store a value like 0.10 exactly, so both accumulate rounding error. For currency, store whole numbers of cents in an integer or use a decimal type. Double is for scientific and engineering work, where a tiny rounding error is acceptable. Let us finish with the most common mistake. You write result equals 0.1 plus 0.2, then check if result equals 0.3. The condition is false. The program silently skips the printf. There is no error and no warning. You might spend an hour hunting for a logic bug that is not in your logic. The fix is an epsilon comparison. Check if the absolute value of result minus 0.3 is smaller than a small epsilon. Let us recap. C has two floating point types. A float uses 32 bits and holds about 7 digits. A double uses 64 bits and holds about 15 digits. Neither type stores most decimals exactly. 0.1 is only an approximation. That is why 0.1 plus 0.2 does not equal 0.3. So never compare floating point values with the double equals sign. Use an epsilon comparison instead. Watch out for the special values, none and infinity. And use double by default. Next, in section 2.4, Operators and Expressions, you will learn how to combine values with arithmetic, relational, and logical operators.